We are on lesson 3 now. This lesson will be on electron configuration. Up until this point, we've been studying elements and the basic properties of atoms, and we've been primarily focusing on Bohr's model of the atom, where you have your nucleus filled with protons and neutrons and electrons that are orbiting the nucleus, sort of in like planetary orbits around a sun, and this works fairly well. But it doesn't show the complete picture of how atoms are designed. And we start to see some of these issues when we begin looking at some of the data generated for elements. And one of the 4 properties we talk about. What we've got here is a little graph that shows us what the different levels of ionization energy are for each element. Now, ionization energy, again, is the amount of energy required to remove an electron, the outermost electron, from a atom, thus forming an ion. We can see that hydrogen is down here, and of course helium, noble gas, is up much higher. Makes sense that it would be much more difficult to remove an electron from a noble gas where it's stable than, say, something from hydrogen, which is not stable. And we can see some of the elements here. Here's the value for lithium, and here is the value for beryllium. But we notice that when it comes time for boron actually has a slightly lower value than beryllium does, and this probably gives us cause for a pause, asking ourselves, well, wait a minute now, we see this general trend that the ionization energy increases as we go across a period from our alkali metals to our noble gases. Alkali metals only have 1 electron to get rid of, but why is it we have these small drops? Beryllium has 2 electrons that it could possibly lose, but boron has 3. Why is it slightly easier for boron to lose its outermost electron than beryllium? Especially when our concept of a model is that electrons exist in these orbitals. In fact, we see this trend again when we compare nitrogen, which is up here, this peak, with oxygen, which comes in right below it. Again, we see this little hiccup in the graph, and we ask ourselves, now, why is this the case? Why do we have these little hiccups? Well, for that, we need to go and actually look at the periodic table. So if we look at the design of the periodic table, we'll get a chance to see exactly why we have this relationship in ionization energies. And it's really interesting to see that this relationship also makes sense. It's based around the orbitals, the actual orbitals that electrons exist in, but the whole design of the periodic table seems to fit this form. Now we've got a block of elements here. These are alkali metals, alkaline earth metals. We have a block of elements here, and of course we have this other block here. It turns out that electrons don't all exist in circular orbitals. We think we've talked about energy levels, but now we need to actually discuss the region of space that the electrons take up, where we've mathematically derived where they should be. It's a probability. It's based on statistics. It's about 95% of the time the electrons are found here, but they don't all live in these spherical shapes. Now here we can see right here an example of a spherical shape. It turns out all of the elements in this block of elements right here, alkali metals, alkaline earth metals, their electrons, outermost electrons, exist in this orbital, this space that's spherical in nature. We call that the S block. And so the outermost electron, so if it was hydrogen, it would be, say, this electron right here. If it was helium, helium would have the one electron here and the other one there, and that would be the 2 electrons in helium in the 1s block, meaning first energy level, and there's 2 s electrons. So we would say the electron configuration for helium would be 1s2, first energy level, s block or spherical orbital, and then there's 2 electrons in there. Now when we come across the periodic table, we'll notice that we have these six elements here, and along the way each element gains an extra electron in its outermost energy level. Now because of this concept of law of charges, we know that like charges repel. And so electrons are always going to feel pressure from the other electrons surrounding the atom. And the more pressure they feel, the higher the energy state they're going to have to exist in. And there's one constant in the universe. Everything tries to get into the lowest energy state possible. So in order for that to happen, electrons need to take up some different shaped orbitals, and they do that in order to maximize their distance away from each other. And this is where we get these dumbbell shaped p orbitals, or the p block. And we can see there's 3 different shapes. We have a set of dumbbells orbitals going across the y-axis, the z-axis, and the x-axis. So 3 dimensions, 3 different shapes. And because we know from helium that only 2 electrons can exist in one orbital, it makes sense that these 6 elements all would have their electrons in the p block, because we can hold 1, 2, 3, 4, 5, 6, a maximum of 6 electrons in the p block, and that would give us our noble gases. That would take us to our noble gases. So when it comes to electron configurations, we can see that the blocks that we find elements in actually pertain to the number of electrons in their outer energy level and the type of orbital that those electrons exist in. Now this is really important. The number of electrons and the orbital that the electrons exist in is actually the main driving force behind the chemical properties of most elements. And so it will turn out that all electrons, all elements in this family, with the exception of hydrogen, of course, lithium, sodium, potassium, rubidium, cesium, and francium, they all have their final electron in an s orbital, and there's only one in that s orbital. Where we see the elements here, the alkaline earth metals, all their outside electrons fill that s block, so they would all end with an s2 electron configuration, because they all have 2 electrons in their outer s block. And so we can begin now to actually figure out what the configuration of all of the electrons for a particular element is. And we can start to look at some of the basic elements here. So when we look at hydrogen, hydrogen has an electron configuration of 1s1. And what does that mean? Well, the first one here deals with the energy level. Now this S pertains to the shape of the orbital, or the type of orbital. And this last one tells you the number of electrons in that orbital. Alright, so we can now start to quickly fly through and look at a whole bunch of different elements. So helium, again, it's in the first energy level, or the first row, so it's going to have a very simple electron configuration. All the electrons are in the first energy level as 1, and then its electrons are also in the s orbital, and it has 2 in that orbital. Now when we go to lithium, we see that lithium has electrons in the first energy level, as 2 of them, and they go in the s orbital. But then it also has electrons in the second, an electron in the second energy level, and it's got 1 electron, and that's in the s orbital. Now beryllium, right beside it, again, same beginning, 1s2, has 2 electrons in the second energy level, and they fill the s orbital. So it's a 2s2. And this is where we're going to see the reason for the hiccups. It's when we compare beryllium to boron. Now boron has 5 electrons that we need to take care of. So 1s2, 2s2, and it's also got 1 p electron. So we say 2p1. Now this is where things get interesting. Beryllium has its outer electrons, the 2 of them, in the 2s2 place, whereas our boron has electrons in the 2s2 orbital and the 2p1 orbital. And this is the one I really want to bring your attention to. If we quickly flip back to the graph, we notice again that beryllium peaks and boron comes in right underneath it. Now why would boron have less energy to remove that outermost electron than beryllium? Well, let's go back to our electron configuration. It would make sense that to take an electron here would be difficult, because we have 2 electrons in the second s orbital. Looks something like this, right? However, when we take a look at removing this electron, we only have 1 electron in a p orbital. And so if we were to draw what the second energy level looks like, we would see this.